In this segment, we briefly review what a student of this signal processing course should know about complex numbers. First of all, consider point C that is located on the xy plane. Let x1 be the x component of C and y1 the y component of C. Thus, the location of point C is exactly specified by its rectangular coordinates x1, y1. A different way of locating point C is using polar coordinates r, theta. Theta is the angle of a vector from the origin to point C, and r is the length of this vector. There is some ambiguity in specifying parameters r and theta. For example, replacing theta with theta plus 2 pi, or replacing theta with theta minus 2 pi, or theta plus any integer multiple of 2 pi, still points to the same point on the plane. Also, r may be replaced with minus r, while theta is replaced with theta plus pi, or with theta minus pi, and the vector still points to C. If needed, we can eliminate this ambiguity by constraining theta to the range minus pi to pi, and r to be non-negative. So, you may ask, what does this have to do with complex numbers? The answer to that question is that every complex number specifies a two-dimensional value, such as the location of point C in a plane using two-dimensional rectangular or polar coordinates. Call the x component of C its real part, and the y component of C its imaginary part. Note that the real and imaginary parts are equally important, because together they specify the location of a point on the plane. The beauty of complex numbers is that a new set of mathematical operations becomes possible to manipulate two-dimensional values that uses similar notation and operations as we use to manipulate one-dimensional values. And, it should be mentioned, some problems such as factoring polynomials cannot be solved without using complex numbers. To make complex number algebra possible, scale the imaginary part of C by j, which represents the square root of -1, and add it to the real part of C to obtain a complex number representation, C equals x1 plus jy1. Because these two terms essentially describe directions that are perpendicular to one another in the xy plane, x1 cannot be combined with jy1. However, when adding together complex numbers C and D, the correct result is obtained by keeping real and imaginary parts separate when combining terms. Rectangular coordinates are better suited for adding or subtracting complex numbers than are polar coordinates. However, multiplication and division of two complex numbers are best done using polar coordinates. Euler's formula is used to convert polar form into rectangular form, and rectangular to polar form conversion is done using trigonometry. Note that this formula for angle theta is accurate only if the point xy lies in the first or the fourth quadrant of the plane. By taking the individual signs of x and y into account, using the two-argument form of inverse tangent, we can recover the principal value of theta, which is in the range minus pi to plus pi. In signal processing, we use complex numbers to simplify notation and to make it more compact, to simplify the mathematical operations, and also to gain insight into linear system behavior by examining the complex valued roots of polynomial expressions. Here are a few important identities to remember. As previously mentioned, Euler's formula, cosine and sine in terms of complex exponentials, magnitude squared of a complex number, and the properties of the complex conjugate operation.